So we know how to make functions. We know how to pass information to them, get stuff back. We know about how calling and returning works. We learned about the stack, and that's where all the local memory lives. We know about references now, those ampersand things that allow us to pass our own memory to somebody else with a different name, and they get to touch our own stuff, which is really nice. We know how to make very large programs and how to make our own libraries now too. All right, so a lot happened that we learned about. Definitely study all that. Let's keep on tracking. All right, let's talk about what are called const parameters. All right, so you can make a const variable, and that means you can't touch it. There's a similar thing for function parameters that I want to show to you. So just like I said before, when you have references, you pass something to a function that took it as a reference, you're allowed to use that memory, first of all, and then also it's not being copied. By using a reference, it's not being copied. Where is that drawing? Like this idea of passing a giant vector. You want to do it by reference so that a copy isn't getting made. You're just working with the original size 1 million vector rather than making a copy of the size 1 million vector. All right? That's the goal. And though when you pass by reference, you're allowed to touch that vector's contents. You're allowed to look at the stuff as well as mess with it. We don't like that sometimes. All right, so that's where const comes in. So maybe we like that memory savings, that lack of copying. We'd like that, but and that's why we use references. But I don't want to like be able to modify that thing. I just want the space savings. All right. So how can we do it? The secret is going to be const, right? Because by passing by reference, you're allowed to mess with things like void. What do we have? Like our increment function can take an int reference. And that actually touches somebody's memory, right? We don't want to be able to do that. Same idea with like a vector. You can pass a vector of like ints to somebody by reference, and then you get to look at the values, and then also maybe change them. If you just want the space savings, you can put a const right out in front of the type name. All right, that's going to be the secret. And so here's kind of why that works, and I'll show you an example in a second. So first of all, you can assign any value into a const. I should prove that to you, okay? Dun, dun, dun. Which should not be weird, in theory. Const.cbp. Just normal const variables. You can do this, right? You can say normal int x equals 42, and then I can say const int y equals x, right? That's not a problem. This makes a constant y, can't change it, but I'm setting it to the value of something that was not constant. Does that make sense? That's totally fine. It's just y can't be changed now. Okay, I can do x++, that's changeable, but y was the const. This won't compile. Okay? So it's unhappy. The same kind of thing works for functions. All right, so let's make, I'll give you that in a second. So remember the interfunction dreamland where things get instantiated, like lines. You have lines that look like this this is the name of your parameter, this is the value you're passing, this is the name of your parameter, this is the value you're passing. You can have a const parameter is what I'm trying to say. Okay, you can pass normal, regular, non-const variables to functions that accept const things, and they will get that thing and it won't be able to be changed. All right, the functions can't change the value that you passed. Okay, so that's perfect when you have references too. So yeah, just like in the future, once I show you this, try to use const references as much as possible because you get the space savings and you're not allowed to touch the memory. Like, it's the best of all the worlds. All right, so a good example of that is like you have a size 1 million vector. You'd like to sum up all the values. You just want to look at the values. You don't want to accidentally like set index 0 to 42 or something. Okay, so let me give you that example. So let me make a vector. So I need the vector library. Vector. And I'll make a vector of ints. And it will hold, doesn't have to be in order or anything, but there's my vector. And I'd like to make a sum vector function that takes v and like sums everything up and gives back the sum. Okay, that's the goal. If I just do normal references, like I want to pass it by reference for sure. So sum vector takes a vector of ints, call it v again. Why not a different v? If I do it like this, it's a copy. We don't like that. If I do the ampersand, it's going to be a reference, so I get the space savings. It's just another name for mains v. Still call it v though. It's not a problem. So let's compute the sum normally. And sum equals 0. Let's go through every element in V. Sum, add it into sum. And then like that's the answer. That's the correct implementation of sum vector, yeah? But I can definitely mess this up. So here's the call to it down here. But I can totally mess this up. I can say this, right? I can do this. V at 0 equals 42 right now. And that obviously is not what it means to sum up a vector, is it? So this will be fine. This will compile, this will run. But of course we're going to get the wrong answer. It's 56, which is completely wrong. Yeah. So we'd like just this line to not even be possible. Okay? We just want to use the vector, not actually touch their contents. Is that a question? Yeah. This is a range-based for loop. It's going through every element of V, and each element gets a chance at being called elem. It'll run the body with elem having being each element. Okay? So go back to the vector slides if you forgot that. That's a fancy. It's just I'm going through all the vector. Elem gets to be the whole vector. One first, then 2, then 3, then 4, then 5. Or I guess 42 first. Yeah. So yeah, we'd like this line to be impossible. Right now it's totally possible. I'm able to mess with that vector. We don't like it. So the secret is, the way you get around this is you say const vector int reference v. Okay, the second you say that, even though I'm passing a normal non-const v, it's going to be converted into one. And so from some vector's perspective, it cannot touch v. All right, and now this line is going to generate a compile time error. All right, so it's like, oh, assignment of read-only location. That's the idea, right? Because everything that's const becomes read-only for the life of that function. So that's beautiful. It won't even compile now. So every time you want to just use something and not be allowed to like change the values, say const. And these references for the space savings. Okay. Yeah. Any questions? Any other questions about this? Is it making sense? Yeah. You mean like this?
Yeah, if I just have that.
Yeah.
And then it's just a parameter.
Mm-hmm.
So because it's still copying over while I'm
Yeah, because when you call the function, it's doing this. It's setting vector int v to be a copy of whatever you passed along, which is mains v, I guess. It's running a line like that. Yeah, that's why we like our references. Exactly. Does that make sense? All right. So yeah, if this were a size 1 million vector, this would be a huge problem. We might run out of memory. So yeah, constant references, save the day, and I hope that is kind of clear. So yeah, just tag a const and also a reference whenever you can. Get rid of it whenever you notice that you actually need to change something. All right. So yeah, that's the secret. I would like to teach you something now that is just like a sneak peek. I want to give you a sneak peek of something that you will learn in CSCI 41 if you're required to take that class, and most of us will be. I am not going to test you, I promise. I'm not going to test you on anything I'm about to say right now. But getting this in the back of your mind and thinking about it now is going to make you do very, very well in CSCI 41, I think. All right, so it's good to show you it now, even though it's going to be a while before you need this knowledge, okay? But keep it in the back of your mind. We're going to talk about the complexity of our algorithms. How fancy are they? How complex? And this kind of leads into like how fast is my program? Because if I have two competing algorithms to do the same thing, there's a complex way and an easy way. Like the complex way is going to take more time, right? We'd like to make our programs fast. That would be nice. So how can we like test two algorithms, like two competing algorithms to do the same thing, two vector sum functions? How do I know which one's better? Well, there's a couple ways. You can use the ctime library. There are some functions there to like get the current time and just do it twice, right, in between a call to some function. And that'll tell you how long it was in between. So that'll tell you like, oh, it took 5 minutes to run this function on this size 1 million vector or something. But unfortunately, like this time is kind of meaningless because I could take an algorithm and run it on my tiny laptop. I could take the same algorithm and run it on your very nice gaming PCs that are worth like 5 times this laptop. And it will run probably several times faster, right? It'll take maybe 1 minute instead of 5 minutes. And so that's not really useful, this kind of timing. And I can take like the algorithm, run it on my phone or run it on my microwave or something, and it'll be even slower probably. So every processor is different. You can't really just like time it. there's got to be a better way to say how fast an algorithm is once and for all, no matter how fast the processor itself is. Because maybe you've like built your own PCs, and like you can buy a 1.5 gigahertz processor, or you could buy a 3 gigahertz processor, and this one's running twice as fast as this one. That's kind of the idea. That's what that means. So there's a better way, and we will look to math to answer this. All right. So instead of processor speeds, because they're different, programs are still going to take the same number of like steps essentially inside of that processor, no matter how fast it is. All right. So if we counted those steps in quotes, then we would get a number that's always going to be the same for our algorithm, regardless of where we want to run it. All right. That's going to be the idea. So let's count what I like to call basic operations for algorithms now. I'm going to teach you how to do that. All right, and that will tell us once and for all how fast our algorithms are, how many steps they'll take on each CPU they could possibly run on. All right, so here are things that are basic operations. They take one step of execution time inside of a processor. It's called a clock cycle. If you're like an engineering major, you've heard of that already. Don't worry, you haven't. We'll get there. So that's the idea. And basic things, the things that your CPU can do in one step of time could be the following. Let's say that your processor it can do an addition on two numbers in the blink of an eye, and one basic operation takes to do that. Same for subtraction, just like basic math. Multiplication takes one step of execution time in your processor. Division, remainder, any kind of comparison, like less than, greater than. Let's pretend that all takes one basic operation, one step of time in any CPU, even the one in your microwave. Okay? Let's say that assignments, those also take one step of execution time, shoving a value into a variable, and then printing to see out as well. Let's pretend that that's going to take one basic operation. All right, that's going to be the idea. So let's do this. All right, so here's two lines of code. It's like a tiny algorithm. Int x equals y times z plus 2. All right, and then we'll see out x. So these are two lines of code. Let's count the basic operations in them, okay? Do you see them all? So we need to get a value and shove it into x eventually. So we got y and z, we got to multiply them. So that's one basic operation, doing that multiplication, right? And then whatever that answer is, we still have to add 2. So the plus on whatever that answer was, that's another basic operation, another step of execution time in our processor, because it's got to like write out all the information and think about it. And then it finally has an answer after it does those two operations. Then it needs to shove that answer into a variable. So that's an assignment. That's a third basic operation. Does that kind of make enough sense? It's a little weird, I know. And then finally, I would like to print x, and we'll say that couting one thing takes one basic operation amount of time. Okay. So there are 4 basic operations in this 2 lines of code. Okay, in this mini algorithm. All right. Things that are not basic are things that kind of depend on the size of something, like a vector. Anything with a loop, right? It's going to repeat. So you can't really just like say once and for all how big it is. So summing a vector, that depends on the size of the vector, right? You do like, you're going to visit every index. And so if it's a size 5 vector, it's a lot faster to sum up everything rather than a size 5 million vector. Yeah. Different amount of work to be done. Calling a function in general is not a single basic operation. You have to like go and figure out what that function was doing, because maybe it's looping again, right? And doing a bunch of things. You have to count the basic operations in the body of that function, in the body of the loop, and kind of like multiply it, okay? Same with like reading a bunch of integers until the user types, like -1, I'm done. You don't know when you're done. That could be infinity, right? So that's not a basic operation. But in general, pretty much every single line of statements in C++ doesn't like call a function that eventually loops. They're made up of like a constant number of basic operations. Okay, so that's 4. And we can do this. We can do this kind of analysis for all of our algorithms, and that will give us once and for all a number, essentially, that tells us how fast it was. All right? And so with that in mind, I'd like you to try counting. All right? It's fine if you get it wrong. It doesn't matter. As long as you're within a constant amount of the truth, it'll be fine. All right? So I'd like you to try this with the people sitting next to you, with this in mind, given what I just did, right? Every little piece of it counts. See if you can count how many basic operations are in this loop. And work together, elect a leader, and please go to the written ice page and tell me what you're thinking. So here is a loop. How many basic operations are in that loop? It will depend on n because we don't know what n is, so n must appear in your answer. All right. Everything else should be whole numbers or n, something involving n. All right. That's my hint. Does that make sense? Give it a try. You have to figure out how many times are each of those pieces going to run. You know all the pieces of a for loop, right? The initialization happens once, then you're going to loop over and repeat a bunch of things. How many times? This is good knowledge for you. Comparisons take one step of execution time. Give you another 2 minutes to think about it. In there. Another minute or so to think about it. How many times? Because things are repeating, right? Things that take a couple basic operations, they're being repeated. If n is 5 versus n being 500, that'll do something, right? So yeah, we need to include n in our calculation. All right, a few more seconds. Get your best guess in if you're feeling brave, or get your answer in if you got it. We'll see what we're thinking. Nice. I see some numbers multiplied by n, and that's going to be very close to the right answer. Good. We're not sure if it's 3n or 4n though. 5n even? Nice. Oh, and a plus 2. I like that. Whoever got that one, that's going to be the right form of the solution, I believe. But nice. Yeah, 5n plus 1, 3n minus 1. That's kind of what we're looking for. All right? So good. Good thoughts. Good job. Make sure you've done attendance. I will stop that soon. Yeah, good job. So let me walk through how I would count this. Honestly, it doesn't matter if you got the answer that I'm about to get, as long as you're within a constant amount of the truth. honestly. That's what you'll learn in CSCI 41. So you don't have to ever do this kind of fine-grained counting, but I need to teach it to you first, all right? So, okay, what's going to happen when we run this loop? What will happen? Well, we run this line exactly once, right? That's the initialization. It only happens once, and it's not actually being looped. It's just one thing that happens. That's only happening once, and it is one basic operation, right? Just shove that one into the I variable. Good to go. That's one basic operation. And then all these bad boys are going to loop, aren't they? So, okay, it's gonna loop. It's gonna run these how many times is the question. All those things. Yeah. Well, I is going from 1 to n. If n is 5, it's running at 5. It's running the body 5 times, right? So it's running the body for sure n times. Yes, that's important. And so like this is going to get repeated. This is going to be repeated at least n times. There's one extra thing that we need to worry about though. We'll get to that. So the comparing two things, one basic operation. The plus, well, let's do the body because it's body then increment, right? The body is outputting both an I as well as an n down. Let's just pretend that they're two separate things, right? When you want to print a single thing to see out, one basic operation. So that's 2 for the full one, for the full line, okay? And then I plus plus. How many basic operations for I plus plus every time you run it? What is I plus plus? It's I equals I plus 1, really. So you both have to do the plus and the assignment after you do the plus. You see that? So it's secretly 2 basic operations. Nice. So, okay. We've got 1 just sitting out there, so it's 1 plus something, right? 1 plus, all these bad boys are going to be repeated because it's condition body increment, and it's running the body n times for sure, right? We're pretending that n is like a whole number. So it's n times all the basic operations for these. 1, 2, 3, 4, 5. Good job, you got 5. Plus 5n. And then, to stop the loop, remember, once we are done with the loop, we have to notice that we're done with the loop. I gets and becomes n plus 1, right? Ooh, excuse me. And then it's too big, right? And this condition has to fail to stop us. So that means this gets run one last time, and that's one basic operation. So plus another 1. So that means our analysis, how many basic operations inside of our CPU does it take to run this loop? 5n plus 2 basic operations. Question? Well, then the loop doesn't run at all, and then you have to do a different kind of analysis. Yeah, this is like worst case analysis, kind of. But yeah, that would be a very good analysis where, like, if n was negative, you'd skip the whole thing and just do the one comparison. Yeah, as well as the increment, or sorry, the initialization. So yeah, that would be a different count. Good. But yeah, pretending it's a normal number. It makes sense. And the idea is, once we come up with this number, it doesn't really matter what you got as long as you're within a constant amount of the truth, because we like to simplify our basic operation counts in computer science. Like the plus 2 when n is big, like pretend n is 5 billion or something. The plus 2 isn't really contributing much. So like we just call this 5n essentially, like we chop off the smaller terms, the ones that don't help us grow too much. And then we just notice like this is, like you add it, if you like print one more thing in this body, it suddenly becomes like 6n. So the 5 versus the 6 doesn't really matter a whole lot. And so we just kind of say this is some constant times n, and that's the analysis, pretty much. Okay? And so as n gets bigger, whatever n was, maybe it was a number we got from the user, do you see how as n gets bigger, we have more work to do, and the graph of how much work we do for each n is kind of like a line. Does that make sense? That's kind of how we analyze it, and this is called the line kind of represents the running time of the algorithm. We say it has a linear running time. You add one extra thing to do, you're doing like a linear amount of new information, a linear amount of new work. Okay, it could be worse, right? It could have been like exponential, but it's just linear, which is nice. Yeah. Oh yeah, this is the symbol. It's really usually done like this, like x. This is what I trying to say here: 5n plus 2, and then 5n. The triple equals means equivalent to. Yeah, I don't know if you've seen that before. Sorry. Yeah, so it just means it's equivalent. We consider this to be equivalent to this to be equivalent to this. Like that's our simplification process. That's the goal. Yeah. Thank you. Any other questions? It's not horrible once you get the hang of it, honestly. And so this is something you'll be doing in CSCI 41. Okay, so that's what we do. We count the basic operations, and then we write some formula for how fast the program was, how many basic operations it takes to run the entire program. And usually our programs are interesting, and they take like input from the user, and like it's a different program every time. Like this one depended on n. Usually our program depends on some variable thing that we get from the user, and we usually just call it capital N when you learn how to do this for real. Okay, so that's kind of the goal. That's the secret. I believe that you could do this for your algorithms. All right, and so like we can like shove into different buckets now different algorithms that we know about that take like more time or less time. So like how long does it take to add two ints always, regardless of whether the ints were 2 and 2 or 2 million and 2 million? Well, they're just two things. You're just doing one plus operation inside of the CPU, so that's one basic operation to add two ints. We call that constant time. It does not matter what the ints actually held. Interesting. How long does it take to sum up n numbers? Well, you're going to do a loop exactly like this, right? Where you'll replace this with like a sum equals sum plus I line, which will also still take two basic operations. So again, it's going to be some constant times n, essentially. Does that make sense? You're doing work per number you're trying to add up. And we call that linear running time, just like I said. Say, your graph of the work you have to do as n gets bigger looks like this. All right? And then what about something else we know how to do? How do we know how to draw an n by n box of stars, right? So essentially, if you think about it long enough, an n by n box of stars, where n was some number that we got from the user, like 5 by 5, 10 by 10, how many stars are you printing, right? In a loop, eventually, deep down, you're printing a single star n squared times. And so it's some constant out in front of like n squared amount of work you need to do. Does that make sense? So this is a harder problem, essentially. This is a harder problem than this one, and we can quantify it now. That's really, really cool. Right? So we call this a polynomial running time. So the graph of how much work you have to do, it gets a little bit more work as n gets larger compared to this one. Right? So if you just take what you just learned and think about all your programs in this way, you are going to do very, very well at CSCI 41. Okay? That's just a sneak peek of all that. Right? I believe that you can do it. It wasn't too horrible, I hope. But that's going to be the main topic of CSCI 41, just like analyzing algorithms all day long. All right? In addition to making new data structures. So yeah, I think that is what I wanted to say about algorithm complexity. Hopefully your brain has not exploded yet. Are we good? All right. So if we're happy, I just have one last thing to talk about. This will be a practice for functions, kind of. I would like to talk to you about how to think about algorithms when you're writing your own, right? I'm going to give you a problem, and soon I won't give you instructions for how to solve the problem. It's your job to figure out the algorithm for it, right? So there's one way to break down an algorithm, and if your problem looks like this, it will be very, very nice, all right? There's one way to break it down into the idea of like state. You're moving state around, like the state is changing of your program. Think about it that way. And then there's also like commands, maybe from the user, that move around you inside of your program and change your state. Right? Certain programs work like this. They don't all, but if they do, it's useful. Like, okay, my program starts in this state, and then through some input from the user, it might go to this state. Like this is what you would notice as you're writing it. It goes to this state with the lines. And then maybe from there, with some extra input, potentially, the program might go to this state, the checkerboard state. All right? And then with some new input, we might just go back to the start and just like do it all over again. So like you might be able to think of your program in this way, where these are like high-level concepts, like we're waiting for a number, we got a number, we're doing some computation with a number, we're ready for the next number, kind of thing. Okay, so yeah, sometimes you can break down your programs like this, and when you can, that helps build a very good algorithm, all right, to solve a problem. So there's what I'm trying to say is I'm going to teach you like a design pattern right now. It's not always going to work, but it's going to be helpful sometimes when it does work. There's a bunch of different ways to write programs. I think you've learned that by now. There's different words for that, like different architectures that you could use to implement your programs. There's different design patterns, and like everybody likes their own way usually. But I'll teach you a cool one, and it will answer this question in the affirmative. Like, is there like some cookie cutter method that if I just follow this, it will make a good program that is objectively beautiful, in my opinion, and that is likely correct. All right? And So yes, there's one way to do it. If you can break down your program like this, sometimes you can build what is called a state machine. And if you program this thing called a state machine, it's pretty hard to get it wrong. All right. So some programs fit into this category can be transformed into a state machine. So here's what a state machine is. It's honestly just a bunch of circles and arrows. That is most of computer science after lower division, honestly. So yeah, these are a bunch of circles and arrows, and they are state machines. So each of the circles is a different state, and I'll talk about what these mean. They're just silly examples that I stole from the internet. So those are states, and all the arrows have words associated with them. Those are called transitions, and they move you between states. They enumerate all the things that you could possibly do in your program, right? They're just spelling out all the operations that can happen inside of your program, right? And it helps you write correct ones. So here's a silly state machine for a very boring person. We're going to model a person inside of the computer, okay? So these are all the three different, there's only three states for this boring person to ever be in, apparently. Very sad. This person could be in the home state, the work state, or the bed state, okay? And there's always a concept of like when the program starts, what state do you start in? So you usually draw an arrow just from nowhere indicating like, okay, let's pretend that this person is born at home. Like that's where they started out their life. And okay, it is time, it's a weekday, it's time to go to work. This person would like to move to the work state. It's not a program, it's just a metaphor, right? It's an example of a state machine, right? But you can pretend it's a program. So you're in the home state right now, you want to move to the work state. There's only one way to do it. You follow this arrow, it's called a transition. You have to take the train to work, right? And that will move you into the work state. Does that kind of make sense? That's the only way you can get to work. And then once work is over, you want to go back to the home state, right? The only way to get there again is to take the same train essentially in the reverse direction. So that'll bring you back to the home state. And then maybe it's nighttime, you have dinner, and then it's time to go to sleep. So you want to go and move into the bed state as this virtual human. And so the only way to move from the home state to the bed state is to follow the sleep transition. Does that make sense? Like that's the only way to get around. That's what our options are right now. And then you wake up and you're back at home and you can do it all over again. So the only ways that you can move around are the ways that are given to you in the state machine. So like you can go home, go to work, go to sleep, wake up, and you can do that a bunch of times if it's a weekday. Maybe sometimes you eat lunch at home. This is something you could do, right? You can take the train to work, go back home, have lunch, go back to work, finish the day, come back home. That's fine. Maybe it's the weekend. You just sleep in bed twice before you go back to work, right? But the nice thing about a state machine is if you can model a program like this, and I'll show you a example of that in a second. If you can model your program like this is enumerating all the things you can do, which explicitly or implicitly, depending on how you think about it, also tells you what you can't do. So notice how there's no way to go to sleep at work, right? There's no transition straight from work to bed. That's impossible. We are not allowing that. Do you see how that's very useful for us as programmers? We've listed all the things you can do, which also lists all the things you cannot do, right? So yeah, you can't go to sleep there. That's kind of the idea, okay? You can't go straight from your bed to work unless apparently this person doesn't work from home, right? That's the idea. So that's a state machine, okay? Just a bunch of circles and arrows, and those can be used to like show all the possibilities of the ways that your program could move around, all right, inside of itself. So here's a better example. It's more complicated though, so I had to do the first one first. This is a good state machine example of how like an Uber app or a Lyft app, ride-sharing app works, all right? So let's pretend that this is its start state. So you've requested a trip on the Uber app or something, and notice how if we ever want to get a driver assigned to us, we must go through the payment state. Do you see how that's very, very important and useful if you're going to program this? You can't get a ride for free right now, right? So you're forced to move through the payment state in order to have a driver assigned to you. You cannot get a ride for free. We are listing that. There's no way to get straight from here to here. That's the goal, all right? That's very powerful, that idea, all right? So, okay, we have to go through the payment stage, and if it fails, you lose the trip, right? You have to put in a new credit card, try again, yeah? But if the payment succeeded, then you get your driver, and then the driver takes you places, and once the trip is complete, the driver is unassigned, ready for new people, and then like you do some like cleanup process inside the app, and then like you go to the trip end state, and like maybe it's a loop that starts all over again. Okay, But that's like a state machine that models how a ride-sharing app works. And notice that it is explicitly saying what you can and can't do. It is impossible if you implement this, right? Imagine that you could implement this. It is impossible to get a free ride. See that? You cannot get to this state before going through this state. We have forced it. And that's really powerful and really cool. And so if you could implement this, it's pretty likely that your program is correct. Does that make sense? There's a way to translate this into code. All right? So it's a bunch of states. You package your program into a bunch of different states and ways to move between those states, potentially on input. Okay? So yeah, those are state machines. States and transitions, circles and arrows. All right? So if you can do that for a program, you'll usually be able to make a correct program the first time, which is a nice thing. All right? So just group your program into states and actions that move you along between states, potentially. All right? So let's have another silly example. Let's model you, my students, as a simple two-state machine. All right? You have two states, as far as I'm concerned. You have a learn state and a practice state that you can be in. All right? So let's say that at the start of class, I didn't assign anything. So you started out as a student in the learn state. Okay? And then I eventually assigned things. Okay? So you're just going to alternate between learn and practice, like when I post new things. So like I give you a lab. And then you move into the practice state. And there's a way, you can have transitions that keep you within the same state. And so as long as your lab is not done, maybe you can stay in that state. It's fine. Not the transition still. And so you'll stay there. And then once lecture starts again, you should stop working and then go back to the learn state and keep learning while the lecture's not over. And so that's kind of like how I could model you as a student. Okay? So your starting state, your initial state was learn. And there's also the concept of where I want you to end up, right? What state should your program end on if you're a student in this class, essentially? This is your state machine. To model which states you'd like to end on, valid states that should be able to stop, right? Your ending states, your final states, you can make a double circle. So the last state that you will be in this class is the practice state, because I will give you the final on the last day. There's nothing left to teach you at that point. You will have practiced, and then your state machine turns off, essentially. All right? So, yeah, that is essentially how you think about a state machine. Does that make sense still? That's you, maybe. All right? So with that in mind, I would like you to try to make a state machine now. So you can break out paint with the people sitting next to you. Try to make a state machine for a traffic light, because this is exactly how traffic lights are programmed. All right? You got a green state, you got a yellow state, and you got a red state. You can't be in multiple at once. So this is a state machine. All right? Every traffic light is a state machine. Try to figure out what is the starting state. Right? If these are the valid states, what's the starting state? Like when you turn on the traffic light, what should happen? What are the transitions that move you between states? Are there ways to go between everyone, or maybe just a few? So try to break out Paint or something. Open up the Paint app and try to draw this, or just break out a piece of paper with the people sitting next to you. See if you can give some names to the transitions that will move you around a state machine for a traffic light. And hopefully your traffic light state machine will keep people safe. Yeah, try that. It'll be useful. Useful knowledge. Yeah, just do it on your own. There's no way for you to turn that in, right? You can't post images of it on the written page. another minute or so to think about it, and then I'll ask for brave souls to tell me some transition names. All right. So yeah, like, what are some transitions? Is there, I don't know. What about the start state? What should happen when like you turn on the traffic light? What do we think? Yeah. I think that's probably the safest option. Good. I would definitely agree with that. If you start all the traffic lights on green, I think that would lead to an issue, right? Somebody else, give me a transition that you guys came up with. New person, so you. Okay. Yeah. So that would be from red to green. Good. Nice. Well, that's perfect. It's like, let's see, like there's a car. Like, how can we sensor? Yeah, sensor detects car waiting, and then like, or even approaching, and then like we should also make sure that no other lights are green right now. No other lights are green. Maybe the car's been waiting for a minute or something. I don't know. So yeah, that's perfect. And then let's see, what else could we do? There's no way to go straight from green to red, is there?
No.
I don't think so. What else? More people, yeah.
The same sensor either detects there's no cars left or enough time has passed for it to stay on green.
Very good. Yeah, so that'll move us to probably yellow, right?
Mm-hmm.
Yeah. Good. So like, I don't know, 30 seconds later, or like cars are gone. Cars gone. They have sensors too. No more cars sensed, and then like then we got to go from yellow to red right after a certain amount of time. And I have learned that it depends on the speed limit of the road, how long the yellow stays yellow. A second for how what? Oh, nice. I would like to know that. Yeah, I don't know. Let's say it's like 3 seconds later. But yeah, that's cool if there's a calculation for it. I like that. That's useful. Makes sense. And then, let's see. Did anybody come up with any other transitions? Any other ways that this traffic light could work? There's technically ways to have it stay in a state. Like, it can blink yellow, right? That's not very common in California, though. It can totally blink red, though, yeah? So it might stay in red if it's, like, on backup power, like there was an electrical failure. And so, just by writing out, just drawing a picture as a programmer, this really helps you enumerate all the possibilities, and it helps you write a more correct program, I think. So yeah, if your program can be made into a state machine, it's all the better, okay? Sometimes this is impossible, but a lot of times it is possible. All right, so yeah, I think that's a good enough example. Does that make enough sense? Hopefully that was fun to draw stuff. All right, so let me show you. Let me take you from start to finish on a program that will count, bless you, that will actually, like, we can make a state machine. I'll show you how to implement a state machine in code, and we'll actually do something useful that is non-trivial that you probably couldn't do without thinking of this problem as a state machine, right? So I'm going to teach you how to count the words in a string. Like you got it for a big long line from the user. I'm going to teach you how to count all the words in it. Like the user gave you some big long sentence or even a paragraph. and you can count all the words in it using a state machine, all right? You might think, like here's the line that you got from the user, you might think that this is a very easy problem, and I'm here to tell you that it is not, all right? You might be like, oh, I'll just count all the spaces, right? If they type every space, I'll go through every character in this line, I'll count every space, and spaces are in between words, so like there's one more word than spaces. Sure, that works until hello, comma, space, I'll leave that for spaces, comma, space, world, exclamation point, space, space, space. If the user starts typing a bunch of spaces, then that whole algorithm goes out the window, doesn't it? So blah underscore, not underscore, but like space. I mean space when I write this little thing, 42. Do you see how it is no longer a trivial problem to count the number of words in this string? All right? That's a problem for us. Let's make it easy on ourselves, though. There's a way to do it with a state machine. And it will always work. All right? The trick is we're going to have a state machine that goes through every character of this string, and we're going to run it on every character, and we will transition based on what we see at each character. All right? Oh, and by the way, this is an algorithm that I learned in my CSCI 40 class when I took it as an undergrad at Fresno State. So this is me passing along this information to you, which is really cool, I think. And so if you ever become a computer science professor, you are now required to teach this in your CSCI 40 class. All right. So here's the secret. You're going to have two states. All right. You're going to be either outside a word or inside a word. All right. And this is going to solve the entire problem. It'll make it very easy. All right. And that's how you have to break it down. And we're going to run each character in our state machine. At the very start, when we turn on the program, we have not given any characters into it. And so we are definitely not inside of any words yet. Okay, so we should start outside of a word in that state. And then, all right, you see the first character. You see the H character, let's say. Let me just draw an arrow and I can keep reusing it. You see the H character. That is a character that is part of some word, right? It's not a space or anything. So you're outside of a word. You just saw a character that is part of a word, yes? So we must transition. So you see a non-space character. You are now inside of a word. Does that make sense? And then, all right, you see the E, the L, the O, the comma. Those are all part of the same word, right? So if you're inside of a word and you see more non-space characters, you are still inside of that same word. Yes? Non-space. But the second you see a space character, you are now not in hello anymore, right? You're in between words. So you are now outside of a word the second you see a space character. Yes? And that's going to be the secret. And then once you go back, right, now it's W. You were over here outside of a word. You just saw a new word, right? So now you're inside. ORLD, you'll stay, right? You'll stay inside of a word until you get to these spaces. Then you'll go back to outside a few times, right? Outside, outside, outside. And then blah, BLH, you're inside, inside, inside. Go to outside, right, with the space. And then you're inside again for 4, then 2. And then that's where you end. Okay? So I claim that once we have this, the problem is pretty much solved. All we need is a count variable that starts at 0, of course, to count words. Which of these, oh, sorry, I need to show you. There's one more, right? If you're here, you're outside of a word, and you see another space, you're still outside of a word, right? Still in between words. So if you see spaces, you stay there. That's what I meant to say. I said it in words, but I didn't draw it, right? So yeah, we're pretty much home free now, because which of these transitions notices a brand new word? You see it? Which non-space? Yeah, so there's this one or this one. Do we all see how, if we're outside of a word and we see a non-space character, we are now inside of a brand new word? Yes, that's the secret. If we just add 1 to our count every time we follow this transition, right there, that's us noticing a new word. And it will work. It's going to be great. All right, so let's watch it work now. So, okay, we're outside of a word. We start outside of a word. We're in the outside of a word state. We see an H. we move, it's a non-space character, so we move to inside of a word and add one to our count. Hello is part of one brand new word. Cool. And then we see the E, the L, the L, the O, the comma, even. Those are still non-space characters. Those are all part of the word hello. Okay? So we stay inside of a word. We're inside of a word right now. We see the space. We were inside. We saw a space. Now we're outside. All right? So now we're in the outside of word state. But we see a non-space character. So that's the start of a new word, right? Because we follow this transition. We saw the W to get here. And so we add one to our count. That's working. Cool. We see the O, R, L, D, exclamation point. We just keep on following that transition. It's not a space. Still inside of a word. And now it's space time. We see one space. So that moves us to outside of a word. All right, so we're no longer part of world anymore. And we're still outside, right? Space, space, space. We stay here, right? We follow this transition. Okay? Haven't seen a new word yet. And then you see blah, the B of blah. You're here. You follow this transition to get here. Okay, there's a new word now. That's the start of a new one. I see some non-space characters, so I'm just part of that same word still. Stay inside. See a space, moved outside. See a 4. Transition over here to inside, that's my fourth word. See a 2, still part of that same word, and that's where I end. Right? Nothing new after that. So do you see how that's going to correctly count that there are 4 words in this sentence? It will always work, no matter how many times the user wants to press space, just to troll with you. Okay? That's beautiful. I love it. So let's code that up. Let me tell you how to translate this into code now. Whee. So, yeah, we're going to read characters one by one and keep track of white space, because maybe it was like some big long file, a string that holds a file. Oh, the internet's unhappy. Let me do that. Maybe it's a string that represents a file name or something, or an entire file, the contents, which has new lines and tabs as well as spaces. That's very confusing. Okay. Yeah, so we want to keep track of just arbitrary white space, and so we will use, right, it's not just space characters, we will use, like, check for tabs and new lines as well, we'll use the is space, right, FCC type for that. And so that's a start. So let's code this up, and do I want to make it a library immediately? Yeah, I think I do. Code up, we're going to make a library for everything. We're going to make 3 separate files, kind of like how we were doing. We're going to make a word counting library that has a header file and an implementation file for just the word counting stuff. And we'll have a main file that has the main function that includes our library and uses it. All right, so 3 files total. And I will do that. I forgot to stop that. Let me do that while I see it still. And then I'll do it in a new folder. How about that? I'll call it count words so it can all be together when you look at it. All right, so I want 3 files. I would like, let's do the header file first, countwords.h. All right. Definitely not that. So I need my header file guards, that's what I meant to do, so that I don't infinitely include myself. And then what do I want in this library? What's my word counting library? What does it need to have? It should just have like a function called count words. I think that's what we'll call it. All right, count words that takes a string s, and it returns how many words were in it, so an int. Okay. So there is some new knowledge here. I need the string library to have strings, right? It includes string. The first thing I need to tell you is remember that header files, whenever you include one, it's going to copy and paste all of this into that file. And so you are not allowed to use namespace standard in a header file. Do not. Or let me do it this way. Do not use namespace standard in a .h file, and then I'll make it all caps. So I'm yelling at you right now. This is very, very important, because the second you say this, using namespace standard, whoever includes you is now using namespace standard, right? Because it's getting copied and pasted into their code. They might not have wanted to use namespace standard. Like, we use it a lot in class, but in the real world, a lot of people do not ever use namespace standard. They always say standard : stuff. So we don't want to force this upon them, all right? So never do that. So if you want a string, you want to access strings, you can include it, that's fine, but you have to fully qualify this guy. Standard : string, right? Remember that from the first day of class? So, okay. So now we have our string, this is the correct type. But what if this string was like the contents of an entire file, right? A big long book, like the entire works of Shakespeare or something. And so we don't want to copy it. Let's see, we don't want to copy it every time we get a string, right? So this is called by value right now. Let's make it call by reference. So I like to just get that, copy it, or not a copy of the string. I like to have the same string, right? Reuse it. And I don't want to be allowed to mess with it either. So it better be a const string reference. All right, so I get my space savings, no copying, but I also can't touch it now. That's the full one that we need here. Okay. And then we can go and we can implement it in countwords.cpp, the corresponding implementation file. And so we'll do customary to include your header file. We don't have to. It's just a good habit to get into. And then we can implement this bad boy. All right. In this implementation file, that's just for us. So we are totally allowed to use namespace standard all we want in our implementation files, if I spell namespace right. Okay. And then that means we can get rid of the standard : here, but never in the header file. Right. And then we can give this an implementation. Let's just do like a stub right now so we can get it working. So there's a very incorrect version of this. And now let's have a main file that includes our header file and uses this thing. Okay? Let's get it all working and then we'll implement this for real. Okay? Let's see here. Let's call it main.cpp. That'll have a main function. It will include our library, our count words library. And so now we have access to the count words function that could take a string and give us back the number of words. And so let's ask the user, hey, give me a line or something. Because we're including this, I don't have to say include string here. That's being pasted. See that? That's perfect because I'm including this file. So I can say string line, and I'll call getLine. CN line. I better ask the user first nicely. Tell them what I'm trying to do here. Go away. Oh, it went away, and there it goes. All right. So cout enter a line of text, colon space. Now I'll get it, and then I'd like to scout how many words are in that line. So count words on whatever was in that string. All right. That's how I want to use the library. Here's its declaration. Now all that's left is to implement that state machine. All right. That's the last piece of the puzzle. Let me show you how. So the secret is going to be, we are in one of two states. We have to keep track of which one we're in, right? We're either in the outside of word state or in the inside of the word state. And so we can just use a variable to keep track of which state we're in. That's all. It's not too bad. So let me show that to you. I will say what state we're in. We start out in a state, and I'll just use a string to represent which state we're in. We start out in the outside state. I'll just use all caps. That's how we can keep track of which state we're in. See how that's not too bad? Like, okay, if it's outside, it means we're in the outside of a word state. If it's inside, it means we're in the inside of a word state. That's really all we need. Then we also need this count variable. Starting at 0. Starts at 0. And then, essentially, right, we have this string. We want to go through all of its characters and run the state machine on all those characters. So, run the state machine on every character in S. And how will we do that? I think I showed you the range-based for loop already today, so let's just use indices this time. Let's do for int I equals 0, I is less than s dot size I plus plus. So I'm going to go through every index of the string and look at every character. So my current character right now is s at I. Yeah? There's my character. I'm looking at it right now. And I need to run that character through this state machine. Right? Either it's a space character or it's a non-space character. So I better use the isSpace function to check if that character is space or not. All right, so I need that from CC type. There now. But honestly, it depends, right? It depends if we're outside what we do versus inside what we do. Okay, so that should be my first check. So am I currently outside of a word or am I inside of a word? It's going to just be this. This really is going to translate into just a nested if else. That's how you run a state machine. That's how you implement it. So we know what state we're in from the state variable. So if the state is outside, run it with that in mind. Otherwise, right, there's only one other state, so I could just say else, just like, okay, that means state was inside. Do one or the other. All right, so if our state was outside, I'm in here. If our current state is outside, I'm in here. And now it depends on Did I see a space character or did I see a non-space character? Yeah, that's my next check. All right. So is that current character a space or not? If current character, is that a space? So if is space current char gives back true, that means it was a space character, right? Otherwise, it was not a space character. This means non-space. All right, and those are my two options. Remember that I said that this is redundant, checking if it's true? So I can get rid of that. It's like if is space returns true. That's how you think about it. If current char is a space, then we'll be here. Otherwise, it's a non-space. What do I do if it's a space? I just stay, right? I stay in my current state, my current outside of a word state. So honestly, you could have an empty body because your state is already guaranteed to be outside. Or just to like keep yourself in check, you can just make a, oops. You just hard code the fact that, oh, I'm still in the outside state. Oops. All right. There, I have the ability to type again. There it goes. This is unnecessary, though, right? But if you see a non-space, that's the important one, right? If you see a non-space character, you better transition to inside a word, and then also add one to our count variable, because that's where you saw a brand new word. So, okay, got to do those two things. So our state becomes inside, and then also count plus plus, right? That count variable that I had up here starting at 0. This was when we just saw, if we're here, if we're outside and we just saw a non-space, that's the transition where we add 1. That's where we saw a brand new word, okay? So yeah, that's the outside state covered. And now what if we're in the inside state? That's the other option. Either we saw a non-space or a space again, all right? So else, now it's pretty much all this all over again, pretty much. More or less, just not adding counts, okay? So if we saw a space character and we were inside, we transitioned to outside, okay? So our state becomes outside. We did that. Otherwise, if we see a non-space character, just do nothing. Just keep your state inside, follow this transition, and you're good to go. Stay inside. So technically, you could have an empty body here as well. Okay, I hope that makes sense. So that's it. And it's going to go and run through every character in the string S, running the state machine each time, potentially adding one to our count when it sees the important place where there's a new word. And yeah, by the time this is done, I'm going to zoom out. By the time all this is done, we've got a value in our count that correctly represents how many words were in that string. So that's what I want to return. All right, not as hard to show you all at once, isn't it? I guess I got to split screen it still. So here is the start of the function. Here is the end of the function. All right, let's try to run it now. And so remember, I got 3 files now. I've got a main function file and another implementation of the library file. Right, the header file, you don't give to G++ because it's being copied and pasted whenever we include. So you say all the CPP files, countwords.cpp and main.cpp, and you can say -o, whatever you want it to be. I'll just say main. So all right, /main, enter a line of text, hello, comma, space, world, exclamation point, 3 spaces, even a tab. That works too, blah, space, 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 tab, 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 42. There are 4 words in that line. Beautiful. It's working. Nice. So are there any questions about how this code is doing the right thing for any string? How this is the translated form of this state machine. That's not horrible, right? It's just like, it makes sense, right? Every state that we're in, keep track of that in a variable. Move around with an if statement. Where are we right now? What did we just see? Okay, bunch of ifs and else's all day long. But yeah, that'll do it. And so all these nice files are working together. Now here's the main function, including our library, using it. Here is the, we'll put it up here. Here's the header file, declares what's in our library, just the one function. And then here is the implementation file that has the whole implementation. Right? So it'll work for whatever you give. Like, I don't know, hello world. What's that sentence with all the words of the alphabet, letters of the alphabet in it? The quick brown fox jumps over the lazy dog. And you can have however many spaces you need, right? Space, 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 tab, 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 then dog. are apparently 11 words in that sentence. And that is correct. All right? So yeah, that's that. We good? All right. Last thing I want to do is, just to get full confidence in our implementation, let's make a test. Make a couple tests, maybe. All right, so we'll do this in the main function file, the main.cpp file. We will, instead of printing stuff and like calling stuff up here in main, let's make tests using assert true. All right, so I'm going to need a copy of that assert true, and I forget where it is. So what's the best way to look for it? Is that a thing? Yeah, cool. It looks like lecture 12 counter main, or lecture 11 testing. That works for me. So I'm going to steal this. I do not need to include string because it's being included from this header file. It's already included there. So string's already there. And so there's assert true. And so now instead of all this, let's change this to just make a test. Call a test. Test count words. All right. So I'll make a little function that packages together a little unit test for my count words function. So I need a string, and I need to call count words on that string. So let's make up one, right? So string s equals hello, comma, space, world, exclamation point, what was it? 3 spaces, blah, and then like new lines and tabs just for good measure, space, 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 42, right? There's still 4 words. And so I'd like to assert, right? Assert true, that if I check the number of words in this string, count words on the string s, better be 4, yeah? It equals 4. And so what's my description of this test? Like count the words in a 4-word sentence. So that's a good test. And you should also be testing any like edge case that you can think of, like count the words in potentially be like a string that's empty. That's a good one. Like make sure it's 0 in a 0-word sentence. Or to be even more subtle, a sentence that only has spaces in it. Still no words, right? Make sure that gives back 0, and it should, the way that we did it. So let's recompile, rerun now. So now what I'm doing is, again, I'm running these tests. That's the only thing that this program is doing now. It's running these 2 tests. And they both pass. Yay, so I'm more confident now that my program is correct. And I'm extra confident because I use the state machine too. All right? So yeah, I think that's all that I wanted to show you. Try to make your own tests. That would be a good exercise, and just like understand what I was doing when I was doing this program, because it's a little complicated. So yeah, I think that's all that I wanted to show you today. Are we good with that? Are there any questions about anything we talked about? Oh yeah, right after this. Give me 2 minutes. It'll all be up there. Yeah. And yeah, I think that's everything. So this was just a straight thing. Let me make sure there's nothing for me to give you today. Yeah, just you have labs out already. Go work on them now. Okay.